This video addresses the topic of atmospheric stability. Now, atmospheric stability, in short, is what determines whether a day will have clear blue skies or whether you will have lots of cloud buildup and eventually thunderstorms. Now, recall from chapter 1 that a lapse rate is the rate of decrease of temperature of the atmosphere with altitude. So if you were to hop in a hot air balloon with a thermometer, fly up to a height of 1 kilometer, whatever the temperature drop is, that is your lapse rate. On average, the environmental lapse rate is 6.5 degrees Celsius every kilometer of altitude. So if the temperature at the surface were, say, 30 degrees, for example, 30 degrees Celsius, hop in a hot air balloon, fly up to an altitude of 1 kilometer, temperature would be 6.5 degrees lower, which would be 23.5 degrees Celsius. Now, remember that this is an average lapse rate, meaning it's not always that number. And the different variations in the environmental lapse rate are what determine whether the atmosphere is stable or unstable. By stability, we are referring to the state of equilibrium in terms of atmospheric movement. In other words, if we have a stable atmosphere, there is no vertical movement in the atmosphere. If we have an unstable atmosphere, then there will be a lot of vertical movement, which leads to cloud development. Consider it this way. Let's say that you have a boulder in a valley. You decide to do some work, push it up the side of the mountain, then you slip. Where does the boulder go? Right back down to where it started. It's the same idea with the atmosphere. If you have a parcel of air and it somehow gets pushed upwards, if the atmosphere is stable, then that parcel of air will come right back down to the ground, will not continue upwards, and so you don't have the means to develop clouds. Whereas if you have a boulder at the top of a mountain and you just give it a slight nudge down the hill, then it's going to keep going and it will not stop. This is unstable equilibrium. The atmosphere if the atmosphere is under unstable equilibrium, then take your parcel of air, lift it a little ways. Well, that parcel will become more and more buoyant and it will just continue upwards. Before we look at the different types of atmospheric stabilities, let's take a quick look at the two different types of adiabatic processes. Now, an adiabatic process is a change in temperature in which there is no interchange of heat. So let's consider you have a bubble of air. It's, thermal is what we called it back in chapter 2. This thermal is warmer than the air around it, so it will rise, and as it rises, it expands and it cools. The rate at which it cools is going to be one of two different numbers. If the relative humidity is less than 100%, we say it's unsaturated air, then it's going to cool at the dry adiabatic lapse rate. That means for every 1 kilometer of altitude that your parcel rises, it cools by 10 degrees Celsius. Now, if your thermal is saturated, in other words, your relative humidity is equal to 100%, then as the thermal cools more, it causes condensation to form, which prevents it from cooling faster. So it's going to cool, in other words, it's going to cool at a slower rate. For every 1 kilometer that your thermal rises, it's only going to cool by 6 degrees Celsius. So these two numbers are the dry adiabatic lapse rate, being unsaturated or relative humidity less than 100%, cooling at a rate of 10 degrees Celsius per kilometer. And if the thermal is saturated, it will have a relative humidity of 100% and will cool at a rate of 6 degrees Celsius per kilometer. Okay, so now we're ready to talk about the different types of atmospheric stability. The first is a stable environment. A stable environment is one in which the environmental lapse rate is less than the moist adiabatic lapse rate. In other words, your lapse rate cools at a rate less than 6 degrees Celsius per kilometer. Now, if this parcel is forced upwards, it will stop moving upwards and will actually start spreading horizontally. This is why the top of a cumulonimbus cloud is very flat, because it reaches the stratosphere, which is a very stable layer. So you have your cloud moving up, it hits the stratosphere, and instead of going further up, it forms this nice flat top to your cumulonimbus cloud. Usually conditions for a stable atmosphere would be because of cool surfaces. You radiate energy away, or advection carries the energy away. Inversions are perfect examples of stable atmospheres. So on the right, let's imagine that you have the environment, which is in the middle. You have the temperature, which is dropping at a rate of 4 degrees Celsius per kilometer, meaning if you start at 30 degrees at the surface, at 1 kilometer your temperature will be 26, 22 at 2 kilometers, 18 at 3 kilometers. Well, now let's somehow, we'll just say magically, take your parcel, an unsaturated parcel, which is less than 100% humidity, and raise it. Remember that the adiabatic rate for dry air, less than 100% humidity, is 10 degrees Celsius per kilometer. So it'll be 20 degrees at 1 kilometer, 10 degrees at 2 kilometers, 0 degrees at 3 kilometers. Likewise, for a moist particle, which cools at 6 degrees Celsius per kilometer, temperature drops from 30 to 24 to 18 to 12. In both cases, your parcel is colder than the environment around you. As a result, you are going to have a tendency for these parcels to be more dense than the environment itself, and so they will sink back down to the ground. On the left is a graph showing the temperature profiles of this figure. You have the environmental lapse rate, which is 4 degrees Celsius per kilometer. And the green is moist lapse rate, and the orange is your dry adiabatic lapse rate. Now, how can you make an atmosphere more stable? Well, that's either done by cooling the surface or warming the air above, or a combination of the both. By doing this, you decrease the difference between layers, and so the temperature, the environmental lapse rate drops because the difference in temperature is smaller. The second type of atmosphere we talk about is the unstable atmosphere. An unstable atmosphere is characterized by an environmental lapse rate greater than both the moist and the dry adiabatic lapse rate. In other words, the environmental lapse rate changes at a rate greater than 10 degrees Celsius per kilometer. Great example of this would be a forest fire, where you are heating up the surface so much that the temperatures are very hot below, very cold above. That's a very large difference in change in temperature. Then the larger the change in temperature, the more unstable the atmosphere is. So same situation. You start off, the environment is 30 degrees at the surface, but now let's cool at a rate of 11 degrees Celsius per kilometer. So you see that in the graph on the left here. That's the red line. And again, remember, the green line is your moist adiabatic lapse rate, and the orange line is your dry. So you have your environment, which drops at 11 degrees Celsius per kilometer, meaning the temperature drops from 30 to 19 to 8 to -3. Well, if you're dry, then the temperature drops from 30 down to 20, 10 to 0. And so up here at 3 kilometers, your dry air is actually going to be warmer than the environment. Likewise, with a moist parcel, if you lift it up higher, temperature drops from 30 to 24 to 18 to 12. In either case, your parcel is warmer than the environment, which is at -3, makes it more buoyant, allows the parcel to continue to lift upwards. How would this be accomplished? Well, you can do this by either warming the surface, increasing the temperature at the surface, or cooling the air aloft, dropping its temperature. Or a combination of both. By doing this, you're going to increase the difference between temperatures in the two layers. And the larger the difference between temperatures, the larger your lapse rate is, the more unstable your atmosphere can be. Now, you'll recall that the stable atmosphere is where the change in temperature is greater than 6, and an unstable temperature, stable atmosphere is when the change in temperature is less than 6, but an unstable atmosphere is where the change in temperature is greater than 10. Well, what about this region between 6 and 10? This is what we call a conditionally unstable atmosphere. Basically, what this turns out to be is that your atmosphere will be stable under one condition, but unstable under another condition. And I'll talk about that in just a second. What we usually see with this is that below a cloud, the atmosphere is actually stable, but above a cloud base, it becomes unstable. Recall that the environmental lapse rate on average is 6.5 degrees Celsius per kilometer. And this lies right in between the 6 and 10 degree range. So our atmosphere on average is actually conditionally unstable. So here is a chart showing the graphs that we had before. So we have here our red line is our environmental lapse rate. And we're going to say that that is right in the middle. So we're going to say 8 degrees Celsius per kilometer. Compare that with your moist adiabatic lapse rate. Well, no matter where you are, the temperature of your moist air parcel is going to be warmer than the environment around it. As a result, your moist air parcel becomes more buoyant. In other words, it becomes more unstable. But if you compare that same point to the dry adiabatic lapse rate, notice that your dry parcel would be colder than the environment around it, in which case it would be more dense, and so it would be a more stable atmosphere. So conditionally unstable atmosphere would be unstable if it's moist or stable if it's dry. So conditionally, with the condition being on humidity, whether your parcel that you lift is moist or dry. So in summary, your moist adiabatic lapse rate, in other words, you take a parcel, you lift it, if it's saturated, it will cool at a rate of 6 degrees Celsius per kilometer. But if your parcel is dry, less than 100% humidity, it will cool at a rate of 10 degrees Celsius per kilometer. Now, the atmosphere will be stable if the environmental lapse rate, what the air around you is doing, is less than 6 degrees Celsius per kilometer. It will be unstable if the environmental lapse rate is greater than 10, and it will be conditionally unstable if it's in the middle. Again, the condition being based on whether it is a moist parcel or dry parcel. Moist becoming more unstable and dry becoming more stable. In the next video, we're going to take this last point here, noting that dew point also changes with height at a rate of 2 degrees Celsius per kilometer. And we're going to look at different triggers that can cause these parcels to be forced upwards and eventually turn into and form clouds.